All right, everybody, this is going to be the properties of water lab. So this lab, I'm probably going to have to do two separate videos for. This first video will be to introduce everything, to revisit the chemistry, the biochemistry of water, and then the next video, we're going to get into the actual lab itself. So let's go ahead and get started. So if you have it pulled up in front of you, I would advise that you follow along as I read through it. So very quickly, water is a polar molecule. Hopefully you know that by now. The oxygen atom in a water molecule has a greater electronegativity, or a stronger pull of electrons, than the two hydrogens it is covalently bonded to. So that's an interesting thing to think about. So we talked about hydrogen bonds in between water molecules, but what kind of bond is in between the hydrogen and the oxygen? Well, the hydrogen is sharing an electron with the oxygen, so it's a covalent bond. So don't let that confuse you. There's a covalent bond in between the H and the O, and then there's a hydrogen bond in between each individual water molecule. As a result, the water molecule ends up having a partially negative charged end near the oxygen and a partially positively charged end near the hydrogens. Much like a magnet, opposite charges will attract and similar ones will repel, so that the slightly negatively charged oxygen of one water molecule will be attracted to the slightly positively charged hydrogens of a neighboring water molecule. This weak attraction and sticking together of polar molecules is called hydrogen bonding. Very important for you to remember. I told you guys we're going to revisit that over and over again. Water is an extremely important molecule in biology. Life came from the earliest watery environments, and thus all life depends upon the unique features of water, which result from its polar nature and stickiness. Some of the unique properties of water that allow life to exist are: 1, it is less dense as a solid than as a liquid. This allows ice to float up and insulates the liquid water underneath the frozen ice sheet. So if you're an aquatic animal that lives in a cold environment, you can survive under the insulation of the ice, because ice floats, becomes less dense. It sticks to itself and causes cohesion. Cohesion is also related to surface tension. It is very important during the process of transpiration, which moves water through the plants. So how does water get from the ground through the roots of a plant all the way up the stem to the leaves and back into the air? Good guess. Cohesion. It sticks to other polar and charged molecules and forms adhesion, which results in a phenomena such as capillary action. It is a great solvent for polar and charged molecules. This is why the blood, which is composed mostly of water, is so good at dissolving and transporting materials. It has a very high specific heat. Water can absorb a great deal of heat energy while displaying only small increases in temperature. This is why water is so good at helping maintain constant body temp. Thank you, water. It has a high heat of vaporization. It takes a lot of energy to make liquid water turn into gas. This is why sweat works so well. It has a neutral pH of 7, which means the concentrations of hydrogens to hydroxide ions are equal. So OH means hydroxide. Okay, next, the statistics. So these are the statistics that we've talked about before, but we're going to get a little more in depth. Statistical analysis is used to collect a sample size of data which can infer what is occurring in the general population. Standard deviation, often reported as plus or minus, shows how much variation there is from the average mean. If data points are close together, the standard deviation will be small. If data points are spread out, the standard deviation will be larger. Typical data will show a normal distribution, what's called a bell curve. In normal distribution, about 68% of values are within 1 standard deviation of the mean. 95% of the values are within 2 standard deviations of the mean, and 99% of the values are within 3 standard deviations of the mean. The formula for standard deviation is below. Okay, so let's scroll down. So here's the formula for standard deviation. Hopefully you've seen it in your notes. Hopefully you've been studying your notes and you've seen it already. So it is a very big formula and looks very complicated. That is why we are going to use calculator. That's why I showed you how to do the calculator first. But the purpose of this box is to break it down step by step so that it makes a little more sense. All right, so just do this just so that you will say that you can say that you've done it. But we're always going to use the calculator. So find the mean. All right, so here are AP Biology quiz grades, 96, 96, 93, and so on. So to find the average, obviously you add them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 numbers, 10 data points. So you add them all up, divide them by 10, and you get your mean. And next it says determine the deviation, which is xi minus x bar squared. From the mean for each value and square it, then add up all the total values. So each xi represents each individual number. So this is the part that's going to take the most time. So you input 96 for xi. You subtract the mean, which is what you calculated here. You then square that number, and then you set that number to the side. And then you do it for 96 again, 96. Put that there. And then you do it for 93. So 93 minus the mean square root. So you go through and you do that for every number. So you're going to have 10 values, and then you're going to add all those values up in the end, and that will give you the deviation. And then the next step is to calculate the degrees of freedom. So the degrees of freedom in this case will be n minus 1. So then what does n represent? Well, it tells you in your notes that n represents sample size. So sample size is how many numbers you have. You have 10 numbers, so 10 minus 1 will be 9. So this value will be 9. So then you take your deviation divided by your degrees of freedom, then you square root it and you get standard deviation. So here's where I did the deviation. Notice how much work that is. This is pretty much the only time you'll have to do it this way, because you'll just do it with a calculator. If you ever do have to calculate it, a lot of times you do not have to calculate it, but anyways, that's sort of what it should look like to find the deviation. So 556.09 is what I got for that number. So then you take that 556.09, and that gives you this top value. You divide that by your n minus 1, so divide that by 9, and you square root the entire thing, and that should give you your standard deviation. And so if you do that, like I said, in the calculator, you should be able to check yourself with that. I checked myself. I got the same number in the calculator as I did when I worked it out. Okay, so in the above problem, the mean is 87. The standard deviation is 8. So 1 standard deviation from the mean would be 79. So you just subtract 8 from 87. That is 1 standard deviation away from your mean through 95. So if you add 8 to 87, you go 95. So we're accounting for a certain range here. We look back up at our bell curve. So if our mean was 87, 87 would be here. 1 standard deviation away from our mean would be here, 79. And then that's 1 minus standard deviation. 1 plus standard deviation would be here, which was 95. So 34.1 plus 34.1, 68% of our data should fall between these numbers. All right. 2 standard deviations would be 71 to 103, which 95% of our data should fall between these numbers. 3 standard deviations would be 63 to 111, which is 99% of the data will fall between those numbers. All right, so remember the purpose of this is to just determine how far your numbers deviate from the mean. Is one more way of analyzing your data. The standard error of the mean is used to represent uncertainty in an estimation of the mean and accounts for both sample size and variability. The formula used to calculate standard error of the mean is shown below. As the standard error grows smaller, the likelihood that the sample mean is an accurate estimation of the population mean increases. So that basically is saying you kind of want to have a smaller standard error of the mean. Using the data from standard deviation example above, the mean is 87 and the standard deviation is 8. Plug in the numbers. Remember that n is 10. The standard error of the mean equals 2.5. This means that the measurements vary by plus or minus 2.5 from the mean. So 2.5 is not an incredibly large number, but if you remember, your mean for the PillBug lab was almost 0. So what does that mean? As the standard error grows smaller, the likelihood that the sample mean is an accurate estimation of the population increases. So if your PillBug standard error of the mean was almost 0, then that sample mean that you calculated is pretty accurate. So 2.5, that's a little bit higher, so that's a little bit less accurate. All right, and then it comes down here, and this will be the last thing for this video. It is common practice to add standard error bars to graphs, marking 2 standard errors above and below each sample mean. All right, so you see here, this is just like what you did in the PillBug lab. You'll be doing the same thing here. The length of the bars shows the spread around the mean. Shorter bars indicate less variability from the mean, while longer bars indicate more variability. All right, so these are error bars. They extend to 1.96 standard error of the mean, either side of the mean. All right, so here you have a lot of variability from the mean, whereas here you have not so much variability. When the range of the bars between groups overlap, this indicates that there is not a statistically significant difference between the means of the data sets. If the range of the bars does not overlap, there may be a significant difference in the means of the data sets. A t-test or other statistical test should be done in order to verify this difference. Or in the case of the PillBug lab, we did a chi-square test. So you did your error bars in the PillBug lab. You determined if there was a significant difference between the means of wet versus dry, and then you did a chi-square to determine whether you reject or fail to reject your null hypothesis. In the figure to the right, we can conclude that the mean IQ of the greenies is significantly different from that of either the reddies or the yellowies. Things are not nearly so clear cut between the reddies and yellowies. Notice how the error bars of the reddies and yellowies overlap, but there's clearly no overlap between either of these groups and the greenies. All right, so there is a significant difference between greenies and reddies and greenies and yellowies, but not reddies and yellowies. So what does that mean? So since there is a great amount of overlap between these error bars for these means, we say there is not a significant difference between the means. So this small difference between the means, or whatever the difference is likely due to chance or error or something else other than the actual variable. So here there's definitely something going on between the IQs between the greenies, reddies, and yellowies. So the next video, we're going to start the actual lab.